Hi, everybody. I hope you are all doing well and that you were able to rest and recuperate over yesterday. Let's see here. So you'll notice down at the bottom on the schedule, I have written that there are some schedule changes that will need to be made to the schedule due to the fact that we skipped yesterday and we're doing yesterday's lecture today. As a result of that, there isn't going to be enough time for labs. So, let me get my pen ready here, and we'll talk about... I don't actually need this on the screen. We can hide that. So let's talk very briefly about some changes to the schedule that will be forthcoming. So, schedule changes. That should say week, but I had a little extra blob in there. So let's see here. Tuesday, Wednesday, Thursday. I made the executive decision to cancel yesterday's lecture due to everything that's been going on to let everybody recover an extra day. So we're going to have lecture today. Tomorrow will also be a lecture, and that'll be pretty normal. On week 9, Tuesday, we'll have another lecture. And then here we'll have lab number 5, as well as the Q&A that we're supposed to be doing today. We'll do it next week. Another lecture. On Monday is midterm 2. Tuesday is the last lecture, and then Wednesday is the last Q&A. And then on Thursday is finals day, which is just, there isn't a class that Thursday. I open the final and you take it at some point during the day. And so that's it. So you'll notice that lab number 6 kind of got pushed off of here because lab number 6 would have gone right here. So there will be no lab number 6. So the last lab that you'll do is lab number 5, which I'll open next week. Lab number 4 is still due tomorrow. Hopefully you have been working on that and have almost finished it up. As well as what? Quiz, is it 7? Yeah, quiz 7 will be due tomorrow as well. Okay. So if you have any questions about this, let me know. I don't plan to update the syllabus because at this point it's like, why bother? It's here. I will make an announcement about it as well. But the syllabus won't be updated, so just please refer to this video in the event that you need to do so. Alright, let me put this back because I'll need it later and I won't know where it is. For tonight's lecture, we're going to do Chapter 8. There's not really much to Chapter 8, but a little bit of this does show up in your lab assignment that you are working on right now, and we don't really cover it in much detail, which is why I dedicated the lab assignment to it. So when we get to osmosis, you're going to be like, oh yeah, I read about all this in the lab. It's pretty much the same thing. And I'll be like, yeah, it is. We're going to do some simple math, and we're going to learn how to make different solutions in the laboratory. In particular, oops, I didn't mean to do that. In particular, this section will show you how to produce something called saline solution, which is what you make in the hospital if you need to administer an IV to somebody and rehydrate them. By the end of Chapter 8, you should know how to do that. Not necessarily how to administer the IV or put it in the bag or whatever, but you'll at least know what the numbers on it mean, and if like there was a catastrophe and you only had table salt and water, like how would you make saline? And you should be able to do that at the end of this. So the first 4 sections, we're going to talk about solubility. This is actually the topic of the lab that you're going to do next week, lab number 5. We're going to put some rules on paper for you to follow. And then we'll talk about how that translates to making solutions out of various components. So the first question we want to ask is, if you make a mixture of 2 substances by pouring one into the other, And the thing that you're pouring in is like a crystalline solid, like, say, sugar or salt. You might see it at the bottom of the container, but if you stir, it goes away. And the question that I have for you is, where does it go? Where does dissolved stuff disappear to? It doesn't go into a vacuum. It doesn't disappear into the ether. It is still there. You certainly would recognize this if you put salt into water and then tasted it. It'd be like, oh, that's really salty, even though you don't see the salt there. Sometimes when you put stuff into a mixture, it doesn't separate out and it doesn't dissolve and you still see it. So, like, for example, this muddy water that I have here, it's very easy to see that there is mud and particulates and stuff in here, and that it's separated out from the majority of the water which is sitting on top of it. We have to differentiate these two things in some way, and so the way that we do that is we use the term soluble and insoluble to describe them. When you add something to a liquid and stir it together, if it dissolves, we call it soluble. If the substance you're adding doesn't dissolve, like it just clumps together and sits at the bottom, or it makes a cloudy solid, or whatever, then we call it insoluble. Things that are soluble will produce a homogeneous solution, whereas things that are insoluble will not. In general, we want to work with soluble solutions, so we need to try and find things... Or, I'm sorry, we want to work with solutions that are homogeneous, so we want to find things that are soluble. Administering stuff that isn't soluble to a person would not be good. You would... I think the term that they use is that you'd clog the line, which is when you put medicines in that make solids and are insoluble, and then you can't administer the medication to the patient. Like, that's obviously not good. You don't want to make solids in their veins. This video that I'm going to show you in a second here is actually one of the videos that is in your lab for next week. And where is the... Is this what I want? Yeah, this is what I want. So if I do this... I mean, I don't really need to expand this, because you can see the whole thing. What we got here... Let's go back to the beginning a little bit here. On the bottom of the screen here is dichloromethane. The formula is for that is CH2Cl2. And what he's pouring on top of it is water. And if you look at this, you'll see that these two things separate from each other. One is not soluble in the other. If they were soluble in each other, you would make one layer. But since they are insoluble, you create two. This is the same thing that happens when you make oil and water and you mix them together. For this next one, he's pouring in hexane, which is C6H14. And you notice that he's pouring it carefully enough so that it doesn't actually go through the water layer into the bottom layer. And as a result, these three things get separated based on the fact that no two touching solutions are soluble in each other. You could do this over and over and over. You could put a bunch of layered liquids together in such a manner such that every other one will be soluble in each other, but the interstitial ones prevent them from mixing. What's happening here now is he's adding iodine, and if iodine dissolves in a liquid, it will turn purple, because the iodine itself is purple. So you can see that when he put the iodine into the hexane layer, the iodine started dissolving, which is why it's changing colors. The next thing he's going to do is he's going to try and knock part of the iodine down into the water layer to see if it'll dissolve there. And what you'll notice happens is that the iodine doesn't want anything to do with the water. It just sort of passes right through. But then it passes down into the dichloromethane layer, and it dissolves in there very easily. Well, that's interesting. Why did the iodine skip the water? Well, that's what I'm going to have you answer in the laboratory. Now, using this bottle that he has probably never used for any other experiment, then specifically this one. It's going to pour all of the stuff into a single container. All the iodine, all the hexane, all the water, and all the dichloromethane. He's going to give it a good shake, and then he's going to pour it back in the graduated cylinder. What you'll notice is that anything that is soluble, now that it's all mixed together, will collect together, and anything that's insoluble will get forced out. So now that the water isn't between the two layers, the dichloromethane and the hexane, which are both soluble in iodine, tend to come together. And so you can see at the very bottom, the water is starting to push itself away from the other liquids. Now, the reason that water is on the bottom now is because water is a higher density than the average of the two liquids. Before we mixed them, dichloromethane was the highest density, so it went on the bottom, then water was in the middle, and then hexane was on the top. But now they've effectively separated from each other, and you can see that all of the stuff that was soluble with iodine was also soluble with itself. So like hexane and dichloromethane mixed together, and they form one layer. So the takeaway message from this is that if you have things that will dissolve in each other, they will all combine. And if you have anything that does not want to dissolve with anything else, you'll make multiple layers. Now, what governs the rules on why hexane wanted to mix with dichloromethane, why it doesn't want to mix with water? You might already know, and I'll give you a hint. It has to do with Chapter 7, when we're talking about intermolecular forces and how molecules interact with each other. And we'll discuss that in more detail as we go through today. First thing we want to do is we want to define what a solution is. Because solutions are going to be the things that we are making, and exploring their properties, it helps us to define it. So the first thing we want to define is the solution as being a mixture of two things. Something is dissolved, and something is dissolved into. The thing that you are putting in is the solute. The substance you are putting something into is the solvent. Now, the combination of those two things together makes the solution. Now, a hard definition that we use is that whichever substance is in greater quantity, that is, there's more of it, we call the solvent. And that's the definition. So if you have 50 grams of something and 100 grams of the other thing, the one that's 100 grams is the solvent. If you have equal amounts, then you just sort of pick one. But it's impossible to be exactly equal. In this class, we will pretty much stick entirely to these two solutions. So the ones... I kind of got them both with my pen there. The ones where the solute is either a solid or a liquid, and the solvent is only a liquid. But any possible combination of phases can constitute... Oh, excuse me. I'm going to make you all yawn. Any possible combination of phases can constitute a homogeneous mixture, provided that such a thing is possible. For example, you can't have a solid solute in a gaseous solution. Like, that's not homogeneous. But if the medium is liquid or solid, you could dissolve particles into it and get a homogeneous solution. So, for example, air is a solution. If you take a deep breath, and then you exhale all that air out, it's just like I did because I'm yawning. I don't know why I'm so tired today. Where was I? Oh yeah, so if you take a deep breath, all of the air that is in your lungs is homogeneous with all the air that was around it. Then when you exhale and you exhale your CO2, that CO2 will distribute through the room evenly, and then eventually the world evenly, and it will stay a homogeneous mixture. You can dissolve gases in water, you can dissolve solids in water, you can dissolve other liquids in water. If you are looking at a solid, you can dissolve any phase you want in the solid. There are all sorts of possible combinations. But for the most part, we're going to stick to the liquid phase for our solvent. Sometimes you will use a solution that doesn't involve water. Most of the time you will use water. Anything that has water as the solvent is called an aqueous solution. And if you don't use water as your solvent, you could use something else. It would be non-aqueous. So ethanol is sometimes used because medicine can be more soluble in it or something like that. And then you'll administer that dropwise, sorry, I should say. And yes, believe it or not, technically alcohol is a solution. The solute is ethanol, and the solvent is water. And together they make a homogeneous mixture. Now, is it the solution? I wouldn't suggest that. In fact, if you think that's the case, you may need to see somebody about counseling. So don't drink too much. But just a little alcohol is fine. Now, how much are you allowed to add before your solution stops being soluble or homogeneous? For every substance, there is some limit to the amount of content that you can put in there. If you put too much, there's not just going to be enough physical space, but the water that is saturating it, there won't be enough molecules, really. I mean, you just have too many particles floating around your solution. How do I want to describe this? I'm trying to avoid talking about recrystallization, because it's kind of beyond the scope of this class. Suffice it to say that depending on a variety of factors, you can only dissolve so much stuff. Now, if you put as much as you can, then this is what happens. You can see at the bottom here of this container that there's a lot of blue solid still undissolved here. Whereas at the top, it is very well dissolved. Anything that is not dissolved is subject to gravity, and it gets pulled to the bottom. Where it just kind of sits there. And what's actually happening, I guess we will talk about recrystallization a little bit, is stuff is dissolving, but redissolving at the same time. And so what we see is that it looks like there's no net change in the amount of solid that is being dissolved. Because the amount that's coming back is the same as the amount that is dissolving. A solution in this state is called saturated, and it cannot hold any more dissolved solute. It just has the most dissolved that it can for its current condition. Now, if I added solid and it dissolved, but I didn't have anything extra at the bottom, this is what it would look like instead. You'd see it as really faint. So this is my dissolved solute in the solution. It made it a little bit blue, but there's no solid at the bottom. Any solution that can potentially hold more solute is called unsaturated. And you may have heard of these words before, saturated and unsaturated, with things like fat. We'll talk more about saturated and unsaturated fats in the lab, but also in Chem 131. Next we want to talk about temperature, I believe. Yeah. Temperature is a major factor that affects solubility. If you heat stuff up, then the rate at which things dissolve increases, and so you can dissolve more of it. When temperature increases, almost every solid out there will become more soluble. And you can see on these curves right here, what we're going to do is we're going to use this one, KNO3, as an example here. because you can actually get some very interesting effects when you are playing around with the combination of temperature and the amount of stuff that you've dissolved in there. So what we're going to do is I'm going to mix a certain amount of stuff together with water. So this is all 100 grams of water. So if I had 100 grams of water in a beaker, and I added some amount of solid at some temperature, this line will predict whether I am soluble or insoluble. Or not soluble, I'm sorry. I am saturated or unsaturated. For example, if I work at 20 degrees Celsius, and I were to add 5 grams of solid, that would put me right here on the graph. Now, if the reference line that I'm looking at, again, is KNO3, I did not hit the maximum amount for this temperature. So that solution would be unsaturated. If I tried to put in 50 grams, then what would happen is that however much that can dissolve, would dissolve, so that'd be like 30, and then the remaining 20 would just stay as solid at the bottom. And so this would be saturated. And so that's how we use this chart. How much stuff can we dissolve? If I choose a number that ends up below the curve, it's unsaturated. If I choose a number that's above the curve, it's saturated, and then any excess just doesn't dissolve. But I don't have to do this action at a given temperature. What I could do is I could do this and then heat up the solution. And that actually leads to something very interesting when we play around with this. For instance, let's suppose that I started here at 30 grams with 20 degrees Celsius. And then what I do is I heat the solution, which means I'm going to move in this direction. To right here. If I have 30 grams at 50 Celsius, well, in theory, I could hold all this. And again, this is for potassium nitrate. So I went from having a solution that was saturated initially to a solution that is now unsaturated, just by heating it. Now let's suppose that I did the opposite of that. If I started here, which is like 85 grams or so, at, what temperature is this? This is 50. It doesn't look like a 50. Hold on. And then I let the solution cool. So now we'd be at like 20 degrees Celsius. If I did this, what would happen? And you can try and type a prediction in the chat, mostly because my chat log is lonely. What do you think would happen if I did this process? So if I started at 50 degrees Celsius after dissolving 85, and I let it cool to 20 degrees Celsius. What would happen? Any idea? Well, there are people here. I can see them. That's a really good prediction. And in most circumstances, you would be correct, because it should just do what we said it would do over here. If I put this much in, it should just go down, right? But in order for something to crystallize, it needs a place to actually do that on. And so if you have solid already in the solution, it'll crystallize really readily. But if you've dissolved everything, then everything is dissolved and there's no way for it to start again. And so you get this metastable sort of situation where it wants to do this, but it needs help. This state is called supersaturated. And we're going to see an example of this in a second. So crystallization needs a place to occur, as in, like, it needs a piece of solid to start crystallizing on. If that isn't available, there's nowhere for the ions to come together, because they're just too far apart, because they're all dissolved. But if we can provide a place for them to be attracted to, then the solid will form, and it will form very quickly. And so we have a demo here for that, and this one I actually really like. Oops. So much that I will just kick it off the screen. Where is... That's not it. Sorry, I gotta find the video that I want for this. That's the one I want. I hit the wrong thing. There we go. Alright, so what I want you to do is, if you look carefully at the reflection in here, you're going to see the scientist preparing the experiment. This is sodium acetate. And sodium acetate is known for being very, very soluble in water at high temperature, but not very soluble at low temperature. As a result, that means it crystallizes really, really easily if you give it help. And so what he's going to do is he's going to put this little tip of a spatula with a crystal on it. He's going to hold it in the middle and watch what happens. So, our solution must have crystallized. It was supersaturated before. All of the ions in the solution come together as soon as they are able to, and they will continue to crystallize until the solution is no longer supersaturated. It'll just go back to being regular or saturated. Now, in this case, the sodium acetate does take up the entire volume of the solution. So the water gets kind of incorporated into the crystal structure. And it doesn't look like there's any water in here, but if you were to crack this open, you'd actually see it. And there's another video that I like to show. Here it is, Fun with Sodium Acetate. You see this in action, because these are all supersaturated solutions, and you can just play with them. Now, when you do this, and you make crystals, it gets really hot. And the reason for that is because creating solids from different phases is exothermic. The energy goes out. You got to take the energy out to make the stuff into a solid. Here is the inside of the solution. You can see when you crack it open, you can actually see the glistening of water. There is water in there. Now, if you pour this stuff, you can make like little towers or things like that. You just have to be very careful about how you pour it, because if it goes up the spigot, like it'll crystallize up faster than it falls down. And if you're not careful, then this will happen, which she's going to demonstrate in a second. Whoops. And then I don't know how you get out of this mess, but yeah. So yeah, that's sodium acetate. And this is all supersaturated solutions that when you disturb them and provide them a place to crystallize, they will crystallize, or they might even start on their own. Oh, I clicked the wrong thing, sorry. Let me just... Woo! That's not what I meant to do, sorry. Alright, so that's pretty much it for solids and solubility. The takeaway here is that as solids are dissolved in your solvent, they will continue to do so and make an unsaturated solution until you hit some upper limit. That upper limit represents the saturated solution. And if you play with temperature, you can increase the solubility, generally speaking. And if you then lower the temperature, you may make a supersaturated solution. And it should crystallize, but unless it has a way to do that, it can't. And that means that it requires like a solid crystal to begin crystallization. Let's talk about gases. Gases actually follow the opposite property with temperature, because gases move faster when you heat them up, and they move slower when you cool them down. Gases dissolve much better if it's cold. This is why you put your soda in the refrigerator when you open it. If you just drink it when it's warm, one, that's gross, and why would you do that? And two, it gets flat really quickly. And the reason for that is because you can see here the CO2 that is in our solution right here tries to move from the soda out of the bottle. And if it's hot, it can do that much more quickly. Now, we put CO2 in this headspace right here. And that CO2 is gaseous. And what that means is that the amount of gas that's up there pushes some CO2 into the solution, which you can then drink because it tastes good. We like the taste of carbonated beverages, right? Almost everybody, I'm sure, has had carbonated water or soda or 7-Up or whatever. And the CO2 that is dissolved in the water makes it acidic and it gives it a little kind of a tart bite to it. So that's all possible because we can actually dissolve stuff in there. Now, if you remove the pressurized gas on top of the solution, and say by opening it, so all of this would then escape, then the amount of stuff that's in solution will also escape too. And as that happens, once all of this is out of the solution, your soda is flat. So pressure increases solubility if the solute is a gas. This is just a diagram about how crystallization occurs and how recrystallization would be the reverse of this. So if water interacts with solute ions, what the water will do is it will try and align around it and then just kind of cart that piece away. And when things dissolve, they just become pieces that float off. So they'll just go off in random directions, carted off by water molecules. Now, if I wanted to recrystallize my stuff, what I would need to do is have this stuff come back. And so I can do the reverse, but I can only do that if there's a place to go to. And so this is the supersaturated situation, which is if you have too much solute in the solution for your given temperature, and you try and recrystallize it, but there's nowhere for it to go, you can't. We got to have some place to put these ions to make a lattice. And if there is no lattice, well, you can't just bump two into each other and make a lattice, because you just need more ions to do that. 2 is a start, but it's a very, very small start. We need much, much, much larger to get things going. This is just IonDipole. This is really just an illustration even more closely of how water is interacting with our ions. So here I'm highlighting the ions. Sodium is positive, so we're going to attract the negative part of water to it. And chloride is negative, so we're going to attract the positive part of water to it based on the polarity of the solution. So when water does this, this is called hydration. When a solvent does this, it's just called solvation. And solvents generally just use their polar parts. So if this is like, say, ethanol or whatever, to align with ions or other components in whatever manner is necessary for them to dissolve. The blue lines in here are called ion-dipole interactions, and they're basically the fourth intermolecular force. I'm not going to test you on ion-dipole interactions, but it's nice to note that they're there because they behave just like dipole-dipole interactions would. It's just that because an ion is a whole charge and a dipole is a partial charge, ion-dipole forces should be stronger, and they are. So in this overview, this is all the reasons why solutions form. All of like the basic gist behind it. We just now need to see the end data. Who has done this experiment? Who has seen what dissolves in what? And can we draw any patterns? And the answer is, yeah, we can. Here's the first pattern. The general rule for solubility is something called like dissolves like. And we're going to use this picture down here to describe this. If I have a bag full of magnetic marbles, and so these are my magnetic marbles, the blue guys. And in the bag, I add to it glass marbles. So the red ones are glass, and the blue ones are magnetic. And let's just assume that I somehow got them into this state. And what I want to do now is I want to shake this in the bag. And what you'd probably say would happen is that all the magnets are attracted to each other, so they're all going to stick to each other. But the glass marbles don't have magnetism in them. They aren't sticky in any way, so they just kind of fall over to the side, or they just get shunted away. And so that's exactly what happens down here in this diagram. And it turns out this is a great analogy for what molecules do. If I have a molecule that is polar, and I give it the opportunity to interact with a nonpolar molecule, or a polar molecule, then this molecule will make the same decision every time. What it will do is it will say, hey, I have a match. Let's make an interaction here. Whereas this side would look at this and go, huh? And nothing would happen. If I put water in this situation, and I say, hey, water, do you want to mix with oil, or do you want to mix with other water molecules? Water always picks itself. And the reason for that is water's polar. So two things that are polar will dissolve each other. Whereas something that is nonpolar will only dissolve other nonpolar things. And so this is where like dissolves like comes from. It refers to the polarity of the substances you're working with. Polar stuff mixes together. Nonpolar stuff mixes together. But if you mix the two, you get two layers and they separate out. Alright, so I think all this text is going to appear behind my description here, so let me do this. There you go. So that's the first rule for solubility, is like dissolves like. If you are given the polarity of a substance, or you can figure it out because you can do Chapter 5 stuff, you draw the molecule and you can figure out is it polar or nonpolar using electronegativity. You can determine whether two things will mix together. Now, this isn't an absolute. This isn't polar is one end and nonpolar is the other. There is a gradient. You can have molecules that are both. Like part of the molecule is polar and part of the molecule is nonpolar. And when you do that, you get interesting things. So, for example, soap is like this. Soap and detergent and stuff that we clean with has a polar part, which dissolves in water, and a nonpolar part, which dissolves in, like, say, grease or grime or dirt or whatever. So when you wash stuff, The polar part is necessary to get it to dissolve in water so you can wash it away. But the non-polar part is necessary to dissolve the grease and stuff that water can't get. Because, again, water isn't going to mix with anything that's non-polar. And most greases and fats and stains that you get on clothing, like, I don't know, grass stains, for example, aren't water-soluble. If you have just solids, for example, like table salt or whatever, salts will make ionic compounds. And ionic compounds, being ions themselves, have a charge. Water, being polar, likes this. But in some cases... Ooh, I don't know why there's this -2 here. Just ignore this right here. Actually, hold on just a second. Let me see if I can fix that. Anyway, if you have an ionic compound, the ionic compound will be soluble in water. There we go. However, some ionic compounds are very strong and are hard to break apart, and then you end up with a situation where essentially the solid doesn't want to dissolve because it's just too strongly bound to itself. And there are many, many different ionic compounds out there. We have summarized some of these into this table and reported what observations we find. And really what you just have to do is you learn how to use the chart. So there are two sections to the chart. There is a soluble section and an insoluble section. And what you want to do is you want to look at whatever ionic compound you are working with and find some feature of it in the ions column. And once you do that, that will tell you whether it's soluble or insoluble, or if you have an exception in which the reverse is true. So let's do an example, and we'll refer back to the chart to answer this. So, will sodium nitrate dissolve in water? So we know that sodium nitrate splits into two pieces. There's sodium, which always has this ion, and there's nitrate, which is this from the list of polyatomic ions that you need to memorize. Now let's go back to the previous slide and look for those things, and I'll write them up here again. So here is sodium, and here is nitrate. Oh, we can see that. Okay, cool. All right. So we got to look for either of those two things. In this example, they're both here. So here is nitrate. Nitrate is always soluble. There are no exceptions. So anything with nitrate in it would be soluble. Sodium is right here, group 1A cations. No exceptions. Anything with sodium in it is always soluble. Anything with nitrate in it is always soluble. So we would go to this slide and we would say, yeah, if you put sodium nitrate in water, it will dissolve. It's soluble. How soluble is it? It's just more than enough that you put even a small amount in will dissolve. So that's the rubric we're using to determine soluble versus insoluble. Something that is insoluble, you put a small amount in and it doesn't dissolve even then. By small, I mean like less than a gram. So now what I want you to do is do the same thing for these two. So look up silver chloride, look at calcium sulfide. These are both in water. Tell me if they dissolve or not using the solubility chart. And then for these, tell me if they will mix with each other by using like dissolves like. You might have to draw the Lewis structure, or you might just have to remember what's polar and what's nonpolar. Or you can just look it up to see if it's polar or nonpolar. Okay? I'm going to give you 5 minutes to play around with the chart. In about a minute or two, I will flip back to this slide here so that you can see it. So go ahead and write these down, and then I'll put it on the screen for you in just a minute. So I'll see you in a bit. Alright, I'm going to change this back to the previous slide. I'll give you a minute to determine soluble or insoluble. Type it in the chat when you think you got it. Alright, how are we all doing? Any questions on this? Do we have the answers? Let's go over the answers here. So I'm going to write these down really quickly on my pad. So give me just a second to do that. So we already did NaNO3 and H2O. Let's do AgC. Oops, AgCl, CaS. And we'll come back to the last two. So if I'm looking at these, and I split this into the two ions that it forms, I know what ion chloride forms. It's minus, because that's always the ion that Cl will form, based on its octet rule. So that means silver must be silver plus. I gotta go look for either of these in the chart here. Let's see if it puts any part of this on the screen that is useful. Nope. So we'll just do that. There's our chart. Do we see anything on here that would be helpful for us in this situation? And it turns out that there's two things that we could do. First one is that we could find... Oh, no, there's only one actually on here. That's the wrong end of the pen. There's just chloride right here. So something with chloride in it is soluble, unless it has silver plus, oh, there you go, mercury 1 or lead 2. So because I have a chloride, the substance should be soluble. But because chloride is paired with silver, it's an exception. And so we would write that this is insoluble. For the next one, I'll just do this. We'll just shove that off the side there. For calcium sulfide, this would split into 2 pieces as well. We know that sulfide makes S2- due to the octet rule. And you also know that calcium does the same as 2+. Let's go look for those in our chart here. Oh, that's not where I wanted that to go. Come back. There, that's the one I wanted to move. So let's look for these. Are calcium or sulfide in this chart at all? I definitely see sulfide down here. Here it is. So sulfides are insoluble unless they're paired with group 1A, ammonium, calcium. There you go. Strontium or barium. These are soluble. So calcium sulfide is therefore soluble. So that's the gist of how you do those sorts of determinations. You look it up on the chart, which again will always be handy for you because you're taking this class online. I can't stop you. You just look it up on the chart. I wouldn't make you memorize this in class. I would provide it to you in any case anyway. So, all right. Finally, going back to this, if we mix these liquids together, will they form one layer or will they separate out? So the way that we do that is we have to determine if they are polar or nonpolar. So water is polar, we know that. If you remember what I said about C's and H's only, anything that has C's and H's only is always nonpolar. And the reason for this is the electronegativity difference between C and H is too small for it to even register on the polar covalent side of things. Remember when we were talking about electronegativity, we care about whether it's less than 0.5, in the middle, or if it's greater than 2. So that just leaves acetone here. And it turns out acetone has this Lewis structure. And so we got this non-polar part on the sides, but this right here in the middle is very polar. So acetone is polar. And now it just becomes a matching game. If they're both polar, they mix together. So polar and polar, that's a match. So this will dissolve. Polar and non-polar, not a match. Those don't dissolve. Non-polar and non-polar will dissolve, though. All right, that's solubility. That's all there is to it. Any questions, let me know in the chat. I think we are due for a break. The next slide should be the next section, right? Yeah, so when we get back, we're going to talk about how to do all of this using some math and figuring out how to represent solutions with quantities, basically. So let's put the title card back up. It's time for a break. Need the timer, which I don't have up. There we go. Let's start that, start the music, and I'll see you in a bit. Oh, so close. That's okay. Alright, so let's continue on to numerical stuff. So now we're going to calculate how to determine concentration. I'm going to give you a few formulas. And your job will be to know when to use which formula, which is actually very easy in this case because they're all denoted with a label that tells you which one to use. So the first formula that we're going to look at is percent by mass. And the way that we're going to determine how much stuff something has is by taking a ratio of how much of the mass of, like, say, A we have relative to the mass of the total. And that's actually just the formula right there. So if I wanted to figure out what percentage of my solution was, say, salt or NaCl, I'd figure out what mass of salt I have, divide by the mass of the solution, and then times by 100% to make a percent. So that's not difficult. We can do that. Now, down here, the mass of the solution is the mass of whatever the components are. So that would be the solvent and the solute added together. Because mass is conserved, if you put stuff in the same container, you could just weigh it before you add it, weigh it after you add it. It doesn't matter. Now, this is a very straightforward formula, so let's put this into practice. So I have 5 grams of sodium hydroxide. I'm going to put that in 100 grams of water. What is the percent by mass? Now, I do want you to try this. There is a wrong answer, though. So be careful not to do the wrong answer. And remember that the formula is mass of solute divided by mass of solution. Wow, that actually saved me a step by doing that way. Okay. So I'll write the formula here. Try and calculate the answer. And I'll go over the answer in just a second. All right, what's the answer? %5 is unfortunately the wrong answer. And now everybody's getting it. Oh no. Let's show you how to get the correct answer. So, first of all, we want to identify what the solute is. What is the solute in my mixture here? So what's the solute? Is it the NaOH? The NaOH. Okay, cool. And there's 5 grams there. What's the solvent? Because the solvent is what you're mixing it into. Yeah, it's the water. There's 100 grams of that. And then what's the solution? The solution is after you have mixed them both, right? So if everything's the solution, and you'll notice that the formula says mass of solution here, what number should go on the bottom? Because it's not 100. Should be 105, yeah. So mass of solute is 5 grams. Mass of the solution is 105 grams instead. These grams go away. And you get slightly less than 5%. That's supposed to be a 4. I don't really know what happened there. There you go. Yeah, the real trick to this is just like knowing the terminology, and then how do I put the numbers into each spot? Because all of the terms start with S. Actually, they all start with SOL. So if you don't know your terms, then that is what you are, is SOL. But if you sit down and just write out everything and like, okay, what is this? What is this? What is this? And then you just match what you need and put it in the right spot. So this is what I need here, and this is what I need here. And there you go. So you're all set now. Oops. I didn't mean to go back to the title. There we go. Now, you'll see right here that I have this label after this. What that label means is percent by mass. But you may also see it written as WW, where they just, the W means weight. And it totally works for either convention. There's no change in the formula or anything. You just might see MM or WW. Alright, so that's percent by mass, and you want to use that when I ask you to find percent by mass. Let's do percent by volume. It's exactly the same, except there's one minor difference. So first of all, the abbreviation for percent by volume is, it's VV, V/V. And you'll notice that the formula is exactly the same, but we're going to look at volumes. And there's one issue that comes up with the volume of the solution. And that volume is not the sum of volumes of solute and solvent. And that might sound really weird to you. If you have 50 milliliters of water and 50 milliliters of alcohol and you add them together, the result that you get is not 100. But I thought that's how numbers worked. What? We're going to see that in this picture right here. Volumes don't actually add together because volume is kind of a weird thing to think about at the atomic level. If you look at these golf balls on the left here, here's the space that the golf balls take up. I'm going to try and paint it in here with the brush. But you'll notice that I have some holes in there. And if I grab a different color, this tinier stuff can fill in those holes. Even though that volume that I'm putting in here was already attributed to the golf balls. And then the rest would just sit on the top. So when you mix two things together that have different sizes, the larger object leaves holes between its molecules, and the smaller thing can fit in those holes. As a result, what ends up happening is that if you have two molecules that are different in very large amounts of size, the volume error that you get is very, very big. If the molecules are very similar in size, you don't get much error. What we're going to look at in the video that I'm going to show you is water and ethanol. And ethanol is quite a bit bigger than water. And as a result, you see something very unusual happen with volumes. The takeaway from all of this is that when you add volumes together, you get an unknown number as the actual result, and I have to tell you what the final volume is. And I also have to tell you to be very specific with how you write procedures. So I won't say add 50 mils of something and add 50 mils of something else. I will say add 50 mils of something and then enough water so that the total is 100. And you'll notice the difference in language that I use there. This should work. There we go. All right. Let me fast forward here. This guy is Gross. No, I'm just kidding. That's his name, George Gross. Ha ha ha. George Gross does this demo where he mixes these two things together, and he has it set up very, very specifically. In the bottles on the left are two 500 milliliter volumetric flasks. One is blue and one is yellow. He's going to fill these with a pipette to the fill line, and you can see the fill line right there. So, oops, sorry, I get my cursor on the screen. Here's the fill line. When the water is right here on the flask, it'll be filled. And when the when the ethanol on this one is filled to the fill line, it will be filled as well. So he's going to do that, and I'm going to fast forward because we don't need to watch him do that, but we can trust that he's doing it correctly. He's going to do that, the same thing to the other one. FYI, the yellow is distilled water, and the blue one is alcohol, or ethanol. Now he's going to pour these together. The reason that they have food coloring added to them is to show that we are indeed mixing them, because blue and yellow should mix to make green, so the end solution should be green. And when he's done doing this, you can see that the bottle he poured from has essentially nothing in it. Okay? So that left bottle is empty. Now we're going to do the same thing with the right. You can see it's turning green. Now this is making a homogeneous mixture, so we are making one solution because there is not two layers separating out. If there were, the colors wouldn't mix. It would just be blue on top of yellow or vice versa. Now when he pours all of this in here, I'm going to pause it again to show you how much is left in the yellow flask, because it should be 0. And you can see that there's nothing in the yellow flask in his hand. And then he's going to set it down. And it's empty. And then when he goes to examine where the fill line is, it wasn't even close. Like, this is probably some 20 milliliters difference. That's like 2% volume just lost. Where did it go? And the answer is, well, it did this sort of thing that you saw on the slide. The blue stuff that I painted over were the golf balls. That's ethanol. And the water was the tinier pieces that fit inside the spaces between ethanol molecules. And the reason that water can do that is because in the volume of ethanol, those holes are part of its volume. we attribute that to as part of the ethanol. If you slide a water molecule in that hole and nothing else moves, then that's one less water molecule you have to put in the end solution, and so it won't take up the total volume. So because of how molecules pack together, you end up with this volume deviation. And the end message is that whenever I give you anything that has volume, I have to tell you the volume of the total solution. I cannot give you the volume of the solute and the volume of the solvent and just say add them together. I have to give you the total. Otherwise, the problem doesn't work. Since volume percent is exactly the same as mass percent, aside from that, I'm going to use the volume of the solution that Wes is going to give me. We're not going to do an example of that one, but we will do an example of this one. This is mass volume percent. Mass volume percent is a little bit different. It has some requirements. And those requirements are that the mass is in grams and that the volume you enter is in milliliters. Okay? If you don't use those units, the formula doesn't work. You get an answer that is not intended. Okay? Mass volume percent is just a weird sort of unit that somebody came up with. They thought, oh, this is convenient, I guess we'll use it. The reason that we care about this, and so the abbreviation for this is MV, you might also see WV. These are the units that saline solution is prepared in. Saline solution in the medical profession, we're going to learn a little bit later, is 0.9% sodium chloride MV. Or in other words, it's 9 grams of sodium chloride in 1,000 milliliters, or 1 liter, of water. And that's enough to rehydrate you safely. So let's do an example of this. Let's suppose that I put 12 grams of water into 50 milliliters of solution. And we'll calculate the mass volume percent of this. So let's put this up here. All right, so let's write down the formula for mass volume percentage. And you'll notice in my language, in the problem statement, I did not say 50 milliliters of water. I said enough water to make 50 milliliters. The reason being, when you add the solid into the water, its volume changes slightly too. So if you have 50 milliliters of water, and then you add 12 grams of solid to it, even though that 12 grams dissolves, it's still taking up space and will displace the water, and you won't have 50 milliliters anymore. You'll have slightly more. So we just simplify that by saying, okay, we're just going to put these things together, and at the end, the total volume will be 50. So let's do the same thing that we did before. So the solute is the NaCl. There's 12 grams of that. Oops, hold on. I gotta do sig figs here. The solvent is H2O. And we don't know how much of that we have because the problem doesn't tell us. But the solution is both. And we know that the volume of that is 50 milliliters. Oops. So now I can take my numbers and just plug them into where they need to go. You're going to notice that the units don't cancel out in this expression, and the funniest thing happens here. We just sort of don't care. so the units just kind of casually disappear. And we don't know where they are. They're just gone. Why do we do that? I don't know, but I hate it. Actually, I do know why we do this, but what we're doing is we're dividing by a reference, and I don't want to get into a discussion about what activity means and like why we do it. But when you're using grams and milliliters in the mass volume percent expression, the units do just go away. They get canceled out by a reference that we're not including. Because we don't need to make the formula more complicated by dividing by 1 multiple times. So you just skip them. What's important anyway is the number, because Canvas won't take units anyway. Now that is way more salt in the water than you would want to administer to somebody by IV. Like, this would dehydrate the hell out of them. If you drank this, you'd get dehydrated. If you drank this, you would hate everything because it would be so salty. You would be salty about drinking this salty water. All right, the last way that we're going to do concentration is actually the most difficult, but it is the one that chemists use the most, so I do need to show it to you, and that's molarity. Molarity is going to use stuff from Chapter 6, specifically how to turn something into moles. And once you have calculated the number of moles you have, you divide by the volume. Here's the formula for molarity. How many moles of solute do you have divided by how many liters of solution do you have? We're going to use molarity for a few sections, and it's just important that you know that it exists. Just like my cat, it's important that I know that he exists, he says. Huh. Oh, you might have been able to hear him. Hi. I'm teaching. Alright, let's do a simple example of molarity. My cat's looking at me like, well, who the hell are you talking to? There's nobody here. So I want to make a solution using these parameters. I want 4.35 moles of potassium permanganate in 750 milliliters of solution. What's the molarity? That's where I want to go. Oops. There is no problem. I didn't mean to move that. Alright, so first thing we gotta do is write down the definition. So molarity. There's the molarity. So let's identify the parts that we have. So we know the number of moles of KMnO4, because I just gave it to you in this problem as moles. And I know the volume of the solution, because that was given to you too. Kresnik, I'm busy. Don't make me throw things at you. Only soft, cushiony things, but it'll startle him and scare him away. So all I gotta do is plug these in here. Hold on. I'm trying to scare him away by clapping at him. It's not working. Go away. Go away. Oh, I know what I'll do. He doesn't like compressed air. There you go. Ah, it's cold. If I can hear him through the headphones, I'm assuming you could hear him too. What do you notice is wrong here? If I just put the volume in as is, I would have the wrong units. So I definitely have to match the units of the formula, because that's how the formula is defined. So this needs to be converted to a volume in liters. Now that we've done that, we can then put the numbers in the formula. So that would be 4.35 moles. Well, we'll say what it is just for good practice. Over this many liters. When I type that in the calculator, I get 5.80 moles per liter KMNO4. And there's the answer. And my cat is already back. Hopefully you hear him. Now, a symbol that we are going to see often for molarity is this, capital M. Capital M just means moles per liter. These are the same thing. You may use either of those designations to indicate molarity in the real world. On Canvas, you're just not going to record units at all. But you might see me write 5.80 capital M, and that's what it means. Now, that's a very easy problem, because I literally gave you the numbers in moles, and I hid the volume as milliliters. That's not hard to do. A more appropriate problem would be something like this, where I give you a mass instead of a number of moles. And so what you'd have to do to solve this problem is you'd have to actually convert to moles. And this is the problem that I want you to work on for a second, while I figure out why the cat is yelling at me. He probably wants to go outside or something, I don't know, or he needs a hug. So using these numbers, 20 grams of sodium hydroxide and 100 milliliters of solution, tell me its molarity. And I'll give you a hint. You'll need a periodic table to solve it. All right, I'll be back after I solve my cat's problems. All right, it turned out my cat needed a hug, so I gave him a hug. My cat is neurotic and will just randomly throughout the day demand attention, and then he'll be sad if I don't give him a hug, so... You know, usually this happens at around 4 a.m. when I'm going to sleep. Hopefully you have the answer. But if not, let's go over the problem anyway here. Oops, that's the wrong problem. Right. I always like to start by writing down the formula. That way I know what I'm looking for in the problem, and then I can try and pick through the problem to get the stuff that I want. Obviously, you need to know what the formula you need is. So for problems like this, it's very easy. There's only one formula that's going to be molarity. It's right here. Oops, I don't know what happened there. I must have hit something weird. So let's see here. So moles of solute. We know that the solute is NaOH. I have a mass of solute. And I can turn grams into moles. And if I do that, that would be the number of moles of solute that I would then put in the formula. Now I have this one memorized. That sodium hydroxide, for whatever reason, is extremely close to 40 grams per mole. That's close enough. So this is the number of moles that I'm going to put in the solution. The volume of the solution is 100 milliliters. If I turn that into liters, that would be this many liters. I'm not sure the work for that anymore, I hope. So now I have my numbers. Here's my volume of solution. Here's my moles. We'll just put them in there. And so the molarity of this should be 5 moles per liter. And that's how you do molarity. All right, so what I'm going to have you do, and this is probably where we'll stop today, is I'm going to give you these problems to try right now. So I want you to tell me what the concentration is for each of these substances as written. So for example, this first one, I'm giving you this specific request. So you need to tell me how to do that from that information. And then you do the same thing for the second one and the third one. Figure out which of the 4 formulas that I've given you should use. And then solve the question. Okay? So I'll give you 5 to 10 minutes to do that. Type in your answers as you get them in the chat so I know how people are doing. And we'll go over them together and we'll call it a day after that. See you in a bit. How are we doing? Any questions? Let me know. All right, I see a few answers on there, so I'm going to hope that we are most of the way through this, so I'm not just interrupting you here. But let's go over the answers. So these... All right, so we got mass percent. I have the wrong color ink, but that's okay. And so the mass of the solute is the AgNO3, so that would be 2.13 grams. The mass of the solution would be both, so when I add them together, I get 30.0 plus 30. Sorry, 2.13 makes 32.1 because of sig figs times by 100%, and I get my phone, which is on top of my calculator. Let's see here, 2.13, 32.1. I got 6.64. All right, so that's MM. I gotta move this guy. What's the mass volume percent of NaNO3? And 100 grams of NaNO3 are dissolved in water to make 1250 milliliters of solution. So same process. So MV is mass solute over volume. Oops, this has got to be in grams of solution in milliliters Mass of my solute is the sodium nitrate. That's 100 grams. The volume of my solution in milliliters is 1250. These units just mysteriously go away. Nobody knows where. I mean, I know where. That's too in detail again for this class. I lost a sig fig. That looks silly. 8.000%. So that's the second one. And then the last one, I gotta set the pen down so I can go back over here and go. I misclicked. There you go. For the last one, we need molarity. And I gave you a mass because I'm a jerk. And so this is glucose. I want to say it's 180.18. I should really look it up, though. Oh, I didn't capitalize a letter. 180.16. That's close enough. Where's my... Here it is. So... (180.16 per mole). So this is the number of moles that are in there, which is 0.1387, so that many. And then, since that's the moles and I know the liters now, I just take that number. I divide by the volume, and the volume was 1.50 liters. Got to put it in liters. And when I do that, I get 0.0927 moles per liter, or 0.0927 capital N. All right. So hopefully you understand the process by which we go through to do these calculations, because you'll be given questions like this where I ask you to tell me the concentration in a specific unit, and your job will be to do the calculation and know which formula to use. Okay. Let me put this up really quick so you have the homework practice on screen. Make sure you pause the video if you need that, because I'm going to go straight to the title card in just a second because we're out of time. I want to thank everybody for showing up today. I realized it was kind of weird having a lecture on Wednesday, but given everything that's been going on, hopefully this is the least weird thing that's been happening, or I guess I should say the most weird thing, because that would mean that you are safe and healthy and doing okay. Thanks for watching. I'll see you tomorrow. We're going to continue and finish Chapter 8. We'll do dilutions and talk about osmosis. We'll probably also start Chapter 9 because the rest of this is very short. Then the quiz will be unlocked and we'll keep going from there. Thanks for watching. Have a good night. Stay safe, stay healthy, stay home.